Everyone, today I will be discussing on survey instruments and calculations, horizontal drilling and multilateral completions. Coming to survey instruments and calculations, in survey instruments I will be discussing drift indicator, magnetic single shot and multi-shot, and measurement while drilling. A drift indicator, or commonly termed as Totco tool, it is used to measure only inclination and it cannot measure azimuth. It comprises of a free hanging plumb bob with a needle at the bottom suspended over a paper disc with concentric circles, which is calibrated in degrees. So you can see that there will be a paper disc which will be having these concentric circles, and each concentric circle will be denoting a particular degree or a particular inclination. There will be a timing device or a motion sensor which actuates the mechanism, and the pin punctures the disc. Okay, so there will be a motion sensor which will actuate this, which will be connected to a timing device, and when this motion sensor gets triggered, then a pin will create a puncture in this paper disc. Okay, and at whatever point this puncture has been created, let's say if the puncture has been created at this point, okay, at this dark point, and then it can be said that my inclination is 4 degree. All right, okay, this motion sensor does not activate the mechanism until the measuring instrument is in rest for a predetermined time period, usually 30 seconds. Okay, so this motion sensor will be triggered when I have stopped my drilling process for, let's say, at least 30 seconds. Then only this motion sensor will be triggered, and as a result the pin will puncture the disc. All right, so this is all about my drift indicator or Totco tool. Now coming to magnetic single shot, it can measure both inclination as well as azimuth. It consists of a camera, a precision floating compass, and a plumb bob type indicator. A camera photographs the plumb bob and the compass face to record both drift as well as direction in a single frame. Okay, so both the drift, that is inclination, as well as the azimuth can be captured in a single frame. Over here the catch is only single photo can be taken at a time. It cannot record compass directions inside a steel pipe or casing because they blank off the earth's magnetic lines or of force. Okay, so we will require a non-magnetic type of a let's say drill collar, where we can house this magnetic single shot. Then only this magnetic single shot can be used to measure the compass direction. Or else if I'm going for a steel pipe or a casing, then we cannot measure this compass direction. It records measurement in the open hole or inside non-magnetic drill collars. All right, so it's very important term over here. It is applicable only in open hole or a non-magnetic drill collar part. So coming to magnetic multi-shot. Magnetic multi-shot instrument record multiple measurements of the drift and direction of the wellbore on a single run into the hole. It is a modified magnetic single shot instruments with a single frame camera replaced by a multi-frame camera. Okay, so as discussed in single shot, only a single frame can be captured, but when we are talking about a multi-shot, then a multiple time you can capture the image. So it always measures the drift angles, but must be in open hole or inside non-magnetic drill collar to measure the compass directions. Again, same thing applies for magnetic multi-shot also. That is, it cannot measure inside a steel casing or a steel pipe, but you require an open hole or a non-magnetic drill collars to measure the drift as well as the compass direction. To measure the compass direction, drift you can measure in the steel casing also, but for compass direction you will require a non-magnetic drill collar or an open hole. All right, so let's move further. Now coming to measurement while drilling, MWD. So MWD is generally housed over here. You can see that this is a typical steerable system. So there will be a drill bit, there will be a bent housing, there will be a mud motor. Okay, so the MWD will be generally housed in a non-magnetic drill collar, NMDC. All right, okay, so this is a typical drilling assembly for a directional assembly. And so you can see that there will be a triaxial magnetometers, there will be triaxial accelerometers. Okay, magnetometer will help us in detecting the azimuth, accelerometers will help us in detecting the inclination. So, and apart from that, there will be pulse generator, telemetry module, gamma module, directional modules, etc., which is present inside a MWD tool. All right, okay, so let's discuss MWD in detail. Now, MWD system allows the driller to gather and transmit information from bottom hole to the surface without interrupting normal drilling operations. So information obtained are directional data, formation characteristics, and drilling parameters. So these three kind of data can be obtained by using a MWD. So in directional data, you can have an inclination, azimuth, and a tool face. In formation characteristics, you can have a gamma ray reading and a resistivity reading. And in drilling parameters, you can have a downhole, weight on bit, torque, and RPM readings. Okay, so these information can be obtained by using MWD. The MWD tool is programmed to make a measurement if the tool is powered up without rotation. The flow through the tool has to be reduced to the amount where the tool shuts off. Okay, so this is a trigger point where MWD will be activated. That is when I am not rotating the string and I am reduced the flow rate through the string. Okay, if these two criteria matches, then my MWD tool will get activated and it will record the reading. So when the flow is again generated, the tools make the necessary measurements and sends them to the surface. The time to take each survey will depend on the startup time of the mud pulsar in the tool and the data rate used to transmit the measurements. When the data is received and the rotation of the string commences. Okay, so after you have recorded everything, then you will start the flow rate. That is, you will start the mud flow through the string, and the data which has been generated will be sent to the surface. Okay, so once the data is received at the surface, then only you can start off with the rotation of the string and continue the drilling process. Now coming to components of MWD, there will be a telemetry channel, transmission system, power source, MWD sensors, and surface systems. Now when you're talking about telemetry channel, you can have an electromagnetic radiation, you can have seismic, mud pulse telemetry, and hardwire. So these kind of telemetry channel you can have. I will be discussing mud pulse telemetry, MPT, in detail. Alright, and MPT is generally used. Now coming to transmission system, you can have a positive, negative, and a continuous wave MPTs. So I will be discussing these three in detail in coming up slide. Power source, you can have a lithium battery or a turbine alternator. MWD sensors. Sensors may include directional sensors, gamma ray, temperature, downhole weight on bit / torque, and RPM sensors also. Now surface system. In the surface system, what you will be doing is recording and interpretation process. Alright, so these are the components of an MWD. Now coming to mud pulse telemetry or MPT, it uses incompressible transmission path mud column to carry the pressure waves created by the downhole sensor. Now three types of MPT can be found, which is positive MPT, negative MPT, and a continuous wave MPT. Okay, now coming to positive MPT, it uses a hydraulic poppet valve to momentarily restrict the flow of mud through an orifice in the tool to generate an increase in pressure in the form of a positive pulse or a pressure wave, which travels back to the surface and is detected at the standpipe. So you can see that there is a hydraulic poppet valve over here. See, there is an hydraulic poppet valve. Here you can see it very clearly. So what it does is that it momentarily creates a restriction. So when this MWD tool gets triggered, at that time this poppet valve, it will restrict the flow. Okay, as a result there is a positive increase in pressure. Alright, so this positive increase in pressure or this pulse of pressure will then be sent to the surface where it gets recorded. Okay, to transmit data to the surface, this valve is operated several times, creating a series of pulses that are detected by the transducer and decoded by the surface computer. I will be creating this kind of a pulse. Okay, this is a positive pulse I'm generating. Okay, so a series of positive pulse will be created like this. Alright, and these pulses will be sent to the surface for recording. Alright, so this is how a positive MPT works. Now coming to negative MPT or a negative mud pulse telemetry, it uses a controlled valve to vent mud momentarily from the interior of the tool into the annulus. This process generates a decrease in the pressure in the form of negative pulse or pressure wave, which travels back to the surface and is detected at the standpipe. Alright, so in negative MPT you can see that there is a control valve where I am venting out mud. See, there is a control valve over here, and momentarily what I'm doing is that I am venting out some sort of a mud, and so because of this venting out of mud, I am creating a negative pulse or negative pressure pulse is created. Alright, so from the graph also you can see a graph of pressure versus time. You can see that when I'm venting out, my pressure will go down. Okay, very important point to be taken into consideration is that positive MPT is commonly preferred because generation of a significant negative pulse require a delta P or a pressure drop across the bottom hole assembly, which reduces hole cleaning capacity of the fluid. Okay, so in the industry also, positive MPTs are commonly preferred because a negative MPT requires high amount of delta P or a pressure drop, which will further reduce the hole cleaning capacity. Again, hole cleaning is a very important criteria when we are drilling in a directional way. Okay, so positive MPTs are commonly preferred. Let's move further. Now, third part, which is continuous wave telemetry. So the transmitter is over here. The transmitter is a rotary valve or a mud siren, which consists of a pair of slotted discs. One of the discs is stationary and other is driven by motor. So you can see that over here, this is a stationary disc, and this is a disc which is attached with the motor. Okay, so this motor will trigger rotation of the disc, and because of this, continuous wave pulses are generated. Okay, so these wave pulses will then be sent to the surface for recording and interpretation. All right, so these are the three kind of MPTs which we have. Now let's move further. Now let's discuss survey calculations. So some of the most common methods used for survey calculation in the industry are tangential method, balanced tangential method, average angle method, radius of curvature method, minimum curvature method. And in this, tangential method is the least accurate one, and radius of curvature and minimum curvature method are the most accurate one. Okay, so the tangential, balanced tangential, and average angle method are based on the trigonometry of a right angle triangle. All right, so let's discuss each and every method in detail. Now coming to tangential method, it uses the inclination and the direction angles measured at the lower end of the survey course length. Okay, so let this be I1 and I2 be the course length or the actual wellbore path. Okay, so what by using this tangential method, I will be using only the lower end point. Okay, that means I will be drawing a tangent from this I2 point. Okay, from that I will be obtaining a right angle triangle. All right, okay, so from the figure you can see that now this AI2, okay, this AI2 will be my new measured depth, because I have assumed the wellbore course length to be this. Okay, so AI2 will be my new measured depth as per tangential method. Okay, and my TVD will be AB, obviously. Okay, or AI2 cos I2. Okay, because I'm considering this as a right angle triangle, so that will be AI2 cos I2, and departure will be BI2. See, departure will be BI2, because over here, since I'm using a tangential method, my new departure will be calculated. All right, and if I want to calculate northing and easting, so my northing will be delta MD or AI2 into sin I2 into cos I2, and easting would be delta MD or delta measured depth into sin I2 into sin A2, where I2 will be inclination and A2 will be my azimuth. All right, so it is clear from the above figure that the tangential method gives a noticeable error in measured depth and departure. It's very obvious, pretty much obvious. Okay, because my actual measured depth will be I1 and I2, the distance between I1 and I2, but by using this tangential method, my new measured depth is AI2, length of AI2. So a noticeable error is obtained. Similarly, my actual departure should have been this. Okay, this has to be my actual departure, but because of I'm going for tangential method, my new departure obtained is BI2. Okay, that is this much. So a noticeable amount of error is obtained when I'm going for a tangential method. All right, now let's move further. Okay, now coming to balanced tangential method. The balanced tangential method uses the inclination and direction angles at the top and bottom of the course length to tangentially balance the two sets of measured angles. So in tangential method, I was using only the lower end point to find out the departure and measured depth. But over here, I will be using, in balanced tangential, I will be using both the ends to get my desired result. Okay, so this method combines the trigonometric functions to provide average inclination and direction angles, which are used in standard computational process. All right, so let I1 and I2 be the 2 points. Okay, I1 and I2 is the actual wellbore path. So I will be obtaining two tangents, that is from I1 I will be obtaining one tangent, and from I2 I will be obtaining second tangent. Okay, and then I will be balancing it out. So by using this, my new delta TVD will be delta MD by 2 into cos I1 plus cos I2. Similarly, my delta north will be equal to delta MD upon 2 into cos I1 into cos A1 plus sin I2 into cos A2. Similarly, delta easting will be equal to delta MD by 2 sin I1 into sin A1 plus sin I2 into sin A2. Alright, so this is how you calculate TVD, northing and easting by using balanced tangential method. This technique provides a smoother curve which should more closely approximate the actual wellbore between two surveys. The longer the distance between the survey stations, the greater the possibility of error. A very important point to be taken into consideration over here. Now, so this is my actual wellbore path, okay, and this is my assumed wellbore path because I am using a balanced tangential method. Now coming to average angle method, when using the average angle method, the inclination and the azimuth at the lower and the upper survey stations are mathematically averaged, and then the wellbore course is assumed to be tangential to the average inclination and azimuth. Alright, so over here, let this I1 and I2 be the actual wellbore path. Okay, so in this average angle, I will be plotting this right angle triangle. Okay, this right angle triangle I will be plotting like this, and from that I will be obtaining whatever parameters that you need to obtain. That is, my delta TVD will be equal to delta MD into cos I1 plus I2 upon 2. My delta north will be equal to delta MD into sin I1 plus I2 upon 2 into cos A1 plus A2 upon 2. And delta easting will be equal to delta MD into sin I1 plus I2 upon 2 into sin A1 plus A2 upon 2. Okay, so this is how you obtain different parameters using average angle method. Alright, now let's move further. Coming to radius of curvature method. The radius of curvature method is currently considered to be one of the most accurate methods available. This method assumes the wellbore course is a smooth curve between the upper and lower survey stations. The curvature of the arc is determined by the survey inclination and azimuth at the upper and lower survey stations as shown in the figure below. The length of the arc between I1 and I2 is the measured depth between surveys. So you can see that this yellow line over here indicates this wellbore path. So this is my station I1 and this is my station I2. Alright, so and this is my horizontal departure. This will be my northing and this will be my easting. My delta TVD will be this. Alright, now these are the formula that how you will obtain these things. So to calculate my delta MD or my delta measured depth, that will be equal to I2 minus I1 upon build rate. So this is the formula to find out my delta MD, and these are the formulas to find out delta TVD, delta northing, delta easting and departure. Okay, so you need to remember these formulas to calculate various numericals. All right, now let's move further. Now coming to minimum curvature method, this method is really a modification of balanced tangential method. Instead of approximating the wellbore path with two straight lines, the minimum curvature replaces these lines with a circular arc. This arc is calculated by using a dogleg scale factor based on the amount of angular change over the course length. The plane of the arc is at an oblique angle. Alright, now so these are the formulas that you will be using to calculate northing, easting and delta TVD. Alright, over here there is a term of RF. Okay, this RF is also termed as ratio factor. To calculate RF, this is the formula that I will be using, where RF is equal to 2 upon theta into tan theta upon 2. Okay, so over here the theta is the dogleg angle. Okay, the theta over here is dogleg angle. Now to find out this theta, so cos theta equal to cos I2 minus I1 minus sin I1 into sin I2 into 1 minus cos A2 minus A1, where A2 is my azimuth and I1 and I2 are my inclinations. Alright, so this is how you calculate various parameters by using minimum curvature method. Alright, now let's move further. I have a numerical related to this survey calculations. So the table gives data from a direction survey. There are 4 points A, B, C, D, and the corresponding measured depth, inclination and azimuth has been given. So we need to calculate my delta MT, delta TVD, departure and northing and easting at points C and D. Okay, so I have used all the 5 survey calculation method to obtain the same. Okay, so let's look at the solution. If I'm using tangential method, then my delta MD over here again will be 400. Delta MD, you can see the difference is 400. Okay, now to calculate delta TVD, this is the formula. I will be placing all the values and I will be obtaining my delta TVD as 365.4 feet. If I want to calculate delta northing, this will be the formula, and delta easting, this will be the formula. Okay, so this is how you obtain various parameters by using tangential method. Now again, if I'm going for a balanced tangential method, as we know, these are the formulas that I will be using, and these are the corresponding values that I will be obtaining by using balanced tangential method. Going with average angle method, you need to remember the formula. So once you know the formula, all you have to do is to place the values. As we know over here, my I1 will be 14, I2 will be 24, that is I1 and I2 are the inclinations, and A1 would be 20 and A2 would be 80. Okay, so all you need to do is to place the values and you will be obtaining the answers. So this is how you obtain average angle method. This is how you obtain delta TVD, delta northing and delta easting by using average angle method. Let's move further. Now going with radius of curvature method, again delta MD, as we know, that will be 400. So this is the formula for delta TVD. My answer would be 377.9. Delta northing, this is the formula. Delta easting, this is the formula. Okay, so you need to remember the formulas. Coming to last method, which is minimum curvature method. First you need to calculate ratio factor. Okay, now to calculate ratio factor, as we know, I need to get my dogleg severity angle. Okay, so this is the formula for finding dogleg severity angle. So my theta will be 20.67, or in radians if I want to express it, it will be 0.3608 radians. Okay, so my ratio factor will be 2 upon theta into tan theta upon 2. 2 upon 0.3602, over here I have used in radians, and tan 20.67 upon 2. Okay, so my ratio factor will be 1.011. So once I have the ratio factor, then all I have to do is to place the values and I will be obtaining the answer. Drilling, let's discuss this. Horizontal wells means when I'm having inclination of 90 degree. Okay, now there are several reasons for drilling horizontal wells, but the most important one is the increased return on investment, ROI. More oil is recovered by horizontal wells compared to vertical wells with the same reservoir parameters and under the same flow conditions. Production rates and volumes must justify the drilling and completion of a horizontal well. Cost of drilling a horizontal well is more than that of a vertical well, and the completion costs are also usually higher. Okay, so this is all about horizontal wells. Let's see why we should go for a horizontal well. So very first thing is increased drainage area. Okay, so let's say this is my vertical well, this is horizontal well, so obviously you can see that my overall drainage area will be very much high when I'm going for a horizontal well. As a result, at smaller delta P, I can obtain larger Q. Okay, at smaller delta P I can obtain larger flow rate, or else in productivity index terms, if I want to say, then my productivity index will increase, because as we know, my productivity index is Q upon delta P. So at smaller delta P I am obtaining larger Q. As a result, my productivity index of the well will increase when I am going for a horizontal well. Alright, so larger and more efficient drainage pattern leading to increased overall reserves recovery. Alright, so this is the first reason. Now coming to second reason, we can prevent gas and water coning problems. So longer horizontal drain hole increases the exposure of the pay zone. So allows a higher production rate at lower drawdown pressure, resulting in less coning. So as I mentioned, if that means at smaller delta P only, I am obtaining larger amount of Q. As a result, as you can see, this is a horizontal well which is placed in this oil pay. Okay, so since I am giving smaller delta P to obtain larger Q, my coning problem is mitigated to a good extent. All right, so this is one of the another advantage if I'm going for horizontal well. So if let's say in vertical well, if I'm going, okay, at same Q, if I want to obtain as I am obtaining from horizontal well, then I have to give larger delta P. Okay, so because of this larger delta P, there will be gas coning and water coning respectively. Alright, so this is the second reason why we should go for horizontal well. Third reason is when I'm having a tight reservoir, at that time compulsorily you need to go for a horizontal well. So tight gas reservoirs characterized with low porosity, that is porosity of less than 10%, and low permeability, that is less than 1 millidarcy of absolute permeability. Small drainage radius and low productivity require significant well stimulation or hydraulic fracture treatment, or the use of horizontal or multilateral wells to produce at economic rates. So production rates from tight reservoirs are quite marginal. Alright, so this is how in a conventional reservoir, this is how a decline or the production profile will look like, and in tight or a shale reservoir, this is how your production profile will look like. So this production profile is production versus time. So you can see that the decline will be like this, but when I'm talking about a tight or a shale reservoir, you can see that there's a drastic reduce in the initial stage itself. Okay, that is the production rate will go down very rapidly at the initial stage itself. So compulsorily you will have to go for a horizontal well, and after horizontal well you will have to go for various well stimulation activities. Okay, so this is a very beautiful schematic which shows that if my reservoir is having greater than 10 millidarcy, okay, then I will have matrix acidization, solvent treatment, and surfactant treatment. All right, and if it is less than 1 millidarcy, if my reservoir is having this much less than 1 millidarcy of absolute permeability, then I will have to compulsorily go for hydraulic fracturing if I'm having a sandstone reservoir, or a acid fracturing if I'm having a limestone reservoir. Okay, so and if the reservoir lies between this 1 to 10 range of millidarcy permeability, then I will have to choose to which well stimulation I have to go for. Coming to fourth point, which is improving the productivity in fractured reservoirs by intersecting a number of vertical fractures. So a vertical well has less chance of intersecting a fracture system compared to that of a horizontal well, and a very significant production increase can be achieved. So you can see that over here I have natural fractures, alright, and if I'm going for a vertical well, then I can intercept only very less amount of natural fractures. Instead, if I'm going for a horizontal well, so you can see that I am able to intersect a large amount of natural fractures. As a result, I can produce more amount of production. Now coming to fifth point, which is a field or reservoir may require fewer horizontal wells for a complete development as compared to other methods of development. As a result, return on investment will be very high. You can see that instead of going for, let's say, 100 number of vertical wells in a particular field, you can go for 20 horizontal wells, and even then also my return on investment will be same for both. Okay, so less amount of investment is required if I am going for a horizontal well. But the catch over here is drilling a horizontal well itself is very costly in nature. Okay, so whether to go for a vertical well or horizontal well, that's depend on the company's policy. Okay, so that's all about the reason why we should go for horizontal well. So let's look at the limitations of horizontal well as well. Now, one major limitation of horizontal well is that only one pay zone can be drained per horizontal well. Yeah, it's a very important point. Only one pay zone can be drained. Okay. However, the development of multilateral technology combined with horizontal technology has increased the possibility of draining several pay zones. Okay. I will be discussing this multilateral technology in coming up slides. Now, second point, which is another technical limitation, is that the horizontal well lengths are based upon drilling techniques and drainage area limitations. The well length and the drainage area dictate whether to drill short or medium or long radius wells. Also, well spacing or closeness to the another operating lease may limit the length of horizontal wells. Okay, so it depends on the type of drilling technique that you are using. I can go for a short radius, long radius, or a medium radius wells. I will be discussing this kind of concept in coming up slides. Third point is cost. The cost is very high, that is up to 1.4 to 3 times more than the vertical well, depending on the drilling and the completion methods used. Okay, it's a very important parameter. The cost is also very high for horizontal well, so we need to be very careful while we are going for horizontal well drilling. Fifth point is high production related problems, and fifth is well spacing. Okay, so these are the 5 limitations that I will be having for a horizontal well. All right, so let's move further. Now let's discuss horizontal well classification. I can have 3 different kind of horizontal wells, which is long radius, medium radius, and short radius. So these are the build-up rate, radius of curvature and curvature. Okay, so for a long radius, my build-up rate will be between 2 to 6 degree per 100 feet. For medium radius, build-up rate will be 6 to 35 degree per 100 feet, and for short radius, it would be 5 to 10 degree per 3 feet. Alright, so and the radius of curvature will be 900 to 290 meters for long radius, 290 to 50 meter for short medium radius, and 12 to 6 meter for short radius. Okay, so this is how your long radius horizontal well will look like. So definitely you can see that it will be much deeper in nature. This is how a medium radius will look like, and this is how a short radius will look like. So you can see that the radius of curvature is reducing. Okay, see, for a long radius my radius of curvature is very high, medium radius it is less, and for short radius it is even lesser. Okay, now long radius method is used in deep reservoirs and when an extended reach from an existing surface location is required. Now medium radius is used to develop reservoirs in shallow depth and require accurate well placements. Coming to short radius method, it is used for recompleting wells or workover and in drilling through low permeability or naturally fractured reservoirs. Okay, so this short radius wells will be used in low depth reservoirs. So we have already seen this formula where my radius of curvature, if I'm asked to find out, so this will be the formula that I will be using, where radius of curvature will be equal to 57.3 into 1 upon build-up rate, or in other terms it is radius of curvature is 180 upon pi theta. Okay, we have already used this kind of formula to calculate various things. Now let's move further. Coming to ERD wells or extended reach wells, this is also another kind of horizontal well where ERD or extended reach well is one in which the ratio of measured depth versus TVD or true vertical depth is at least 2:1. Okay, that is measured depth upon TVD will be always greater than equal to 2:1. Okay, now the advantages of having an ERD well is increased horizontal displacement from central platform, increased penetration length of reservoir, require less number of wells to develop a field, and require less number of platforms to develop a field in offshore. Okay, so these ERD wells are generally found in offshore, and these are the advantages of having ERD wells. Okay, so you can see that in this figure, this depicts, let's say, for a traditional well, by using traditional horizontal well also, I will be obtaining this kind of a profile. Okay, but if I'm going for an ERD well, then you can see that from a long range only I can intercept my target because I'm going for an ERD well. Again, important point is my MD, that is my measured depth to TVD ratio, should be at least 2:1. All right. Okay. So these are the advantages of having an ERD well. Let's discuss multilateral wells in this particular slide. Advantages of multilateral wells: it can drain more than one reservoir at a time and ideal for multi-late reservoir. Okay, so you can see that by using multilateral wells I am able to drain all these 4 reservoirs. Okay, 1 2 3 4. Okay, so that's one of the advantages. And second is reduction in number of platforms required. Again, a very important point. That means from a single platform only I can go for multiple wells. Okay, so this is also termed as pad drilling. Okay, so these are the two advantages of multilateral wells. Now TAML classification, that is technology advancement multilateral classification. Okay, so based on this TAML classification, it has given 6 different kind of multilaterals. Okay, and it is based on junction type. So junction completion is key to build up section of the well. Okay, so 6 different levels has been given. So level 1 is the simplest type of a multilateral, and level 6 is the most complex type of multilateral well. Okay, let's discuss each and every multilateral in detail. Okay, so in level 1 you can see that this is a motherboard and this is the lateral section, and you can see that both motherboard as well as my lateral section is kept open, and that is, or in other words, it is barefoot in nature. Okay, now in coming to second point, which is over here my motherboard has been cased and cemented but my lateral is kept open, or a slotted liner is kept. Okay, so this is the second type of a classification. Now third TAML classification is over here my motherboard and is cased and cemented and my lateral is cased but not cemented. Okay, so here you can see that in this figure you can very clearly see. Now coming to fourth point, where my motherboard and my lateral has been cased and cemented, but you can see that, let's say, this is the production from my motherboard and this is my production from the lateral section. Okay, At this junction point, both the production will get mixed up, and from a single tubing only you will be producing at the surface. Okay, so this is the fourth kind of classification of multilateral. Now coming to fifth point, where similar to fourth point only, you can see, but I will be having two different production strings. Okay, that is from motherboard I will be having a different kind of a production string, and from lateral I will be having a different kind of a production string or a tubing. Okay, and at the surface I will be obtaining a production from both the strings. Okay, that is both the string differently. Kind of a multilateral, I am obtaining production from two different strings. Okay, so I am having a better pressure integrity at this junction using straddle packers for that. Okay, now sixth kind of a multilateral completion. Over here I am having a good pressure integrity at the surface. So in integral mechanical casing, seal or cement alone is not sufficient. It includes reformable junctions as well as non-reformable full diameter splitters that require larger diameter wellbores. Okay, so this is a more advanced kind of a multilateral completion where I can have a reformable junctions. Okay, so in above all these 5 points, that is from level 1 to 5, I was having non-reformable junctions, but in level 6 I am having a reformable junction. Okay, and I am having a better pressure integrity as well as mechanical integrity when I'm talking about sixth kind of a level of multilateral. Okay, all right, so that's all about directional drilling. So hope all of you have understood directional drilling in detail. Thank you and Jai Hind.